Okay, let's begin. You see this is working. That's good. This is the second week of classes, technically. So we've got discussion sections today and tomorrow. At the end of tomorrow's discussion sections, we'll be moving students off the wait list into the class to the extent that we can. We've waited this long because we want to give students a chance to discover they don't want to be in this class and tell us that, or to confirm that they really want to be on the wait list. We will do everything we can to get as many of you as possible into the class, but there are certain limits. We have to give preference to psych and cog-sci majors. We have to give preference to seniors and juniors. It's just the way things go. After that, we'll do it by order on the wait list to the maximum extent possible. But the thing is, you gotta be on a wait list for which there are open seats. If you're waitlisted for a section that's closed because it's filled, there isn't anything I can do for you, okay? Or the GSIs for that matter. So there's going to be a little bit of shuffling, and while it's true that there can be informal arrangements, there are limits to that too, because there are only so many seats in a room, and the fire marshal will only allow us to move X number of seats from one room to another. So we're working under a bunch of constraints. But we're going to try to do all of this shifting at once, beginning Friday, so as to relieve pressure on the student services offices for psych and cog-sci, who have to do all of this by hand. Okay? So if you want to maximize your likelihood of getting in the course, be a senior or junior cog-sci or psych major, and be waitlisted for a discussion section that actually might have some seats open. If you're number 25 for a discussion section that's full, that's not going to work. Okay? It's not going to work. Okay, anything else structurally about the course, organization, format, anything like that? Again, my apologies for the webcast last time. Missed about 15 minutes, but those of you who were here know that nothing much went on those 15 minutes anyway. Okay. In what I think is the best paper ever to be written about consciousness, the kind of paper you'd sell your grandmother to have written. Thomas Nagel, philosopher at NYU, described consciousness in terms of there being something that it's like to be conscious, okay? And the general argument is there's something that it's like to see something as opposed to hear something. There's something that it's like to see blue as opposed to red. There's something that it's like to be a conscious human or a conscious chimpanzee or a conscious aplysia, if aplysia are conscious. But the implication is there's nothing it's like to be a podium or a desk or a window or a rock or a tectonic plate. That's the difference between something that's got consciousness and something that doesn't. Now that's debatable, and you'll see when we talk about mind, philosophical approaches to mind and body, there are people out there who actually think that thermostats and solar systems are conscious. But right now, let's not go there. Instead, if you want to read a really nice paper, this is great bathtub reading. Nagel's a wonderful writer. I really recommend this paper for you. But the general idea here is, fundamentally, an organism has conscious mental states if and only if there is something that it's like to be that organism, something that it's like for that organism, to be that organism, okay? So there's something that's like for me to be a turkey, for something to be a turkey, because I can eat it, but the question about turkey consciousness is there something that's like to be a turkey for the turkey, right? Okay, one way in which we talk about what it's like to be conscious, or what it's like to have certain kinds of experiences, returns to our old philosophical notion of qualia. By qualia, remember, we're talking about these qualities of conscious experience. The quality that makes seeing different from hearing. The quality that makes seeing red different from hearing, from seeing blue. Qualia are, as Dennett reminded us, indescribable and ineffable and all sorts of good things. So it's hard to convey the idea of qualia more than with this kind of standard philosophical definition. But the general idea is that qualia have to do with what it's like to see red or blue, to hear something, to see something, or whatever. Quick question. Well, I can't dim these lights, I don't think. I can do, see if I dim all these lights, we get that. So I got to do something. What can I do? Can I do that? Is that better? Is that even better? No, this is better. Okay, that's what we'll do from now on. All right, thank you. All right, so what we're going to do today is to talk about qualia and how the problem of qualia can be approached scientifically. And this basically is, it is the work of two disciplines known as sensory psychophysics, a psychological discipline, and sensory neurophysiology, a biological field. And let's first take up the question of basic sensory modalities, what it's like to see something as opposed to hear something, and try to figure out exactly how many such qualia there are. Aristotle, that's Aristotle, gave us one answer. He said there are 5 different modalities of sensation: vision, audition, gustation, olfaction, and the tactile sense, seeing, hearing, tasting, smelling, and the sense of touch. A physiologist named Sherrington, right at the early part of the 20th century, argued for a somewhat expanded list of sensory modalities, first classified in terms of exteroception versus proprioception. Exteroception is the sensation of objects outside the body. Proprioception is sensation of objects inside the body, objects and events inside the body. Then there are these distance senses where the stimulus doesn't make contact with the body. The distal stimulus doesn't. Like vision and audition, you're out there, okay? You're not touching me. The chemical senses, where what's at root in the sensation is some kind of chemical reaction. The skin senses, where there is contact between the stimulus and the body. And then proprioception is basically the sensation of bodily movements and orientation. Kinesthesis, what you feel when you're moving around in space. Equilibrium, what you feel when you're more or less balanced. Now, Sherrington also talked about a third broad category of sensory modalities, what he called interoception. We're not going to talk about those, at least not seriously. These qualify as sensory mechanisms in the sense that there is some kind of afferent activity that sends information from one part of the body to another, but they don't give rise to conscious sensations, at least not in the usual sense. So, for example, in homeostatic regulation, you've got sensors that keep track of the amount of fluid in your cells, and that sends signals to the central nervous system and gives rise to the urge to drink, to compensate, to resupply those cells. But yeah, we're conscious of sensation, but we're not conscious of cell fluid levels. Similarly, there are ocular cues to things like distance. When I focus on an object in the back of the room, my eyes are essentially parallel with each other. When I focus on an object in the front of the room, they turn inward. That is, the musculature in the eyes sends information to the visual system that tells me what my eyes are doing, but I'm not consciously aware of that. It's sensation in some sense, but it's not conscious sensation, and we're not really going to talk about that at all afterwards. So anyway, there are these 9 modalities of sensation, not 5. And the question is, how do we know? Well, since Sherrington, we've argued that every different modality of sensation can be defined objectively in terms of a package of 4 features. There's a particular, what's known as the proximal stimulus. For vision, that's light waves emanating from an object and falling on the retina of the eye. Then there's a sensory receptor, the rods and cones embedded in the eye that are stimulated by that electromagnetic radiation. Then there's a sensory tract, like the optic nerve, that carries neural impulses from the sensory receptors in towards the central nervous system. And then there's a sensory projection area somewhere in the brain, like the occipital cortex, which is right back here, which is where visual signals end up. Johannes Müller, 19th century German physiologist and psychologist, packaged this all in terms of what's come to be known as the doctrine of specific nerve energies. And what the doctrine of specific nerve energies says is that each different sensory modality is associated with a different neural system. Okay? So you've got the optic nerve for vision, you've got the auditory nerve for audition. You've got the occipital cortex for vision, you've got the temporal cortex for audition, and so on. So what gives rise to a particular sensation of seeing something or hearing something or smelling something or tasting something is not so much in the stimulus itself. In fact, it's not in the stimulus at all, but rather in the activity of certain neural structures. They give rise to these conscious sensations. The proof of this is that you can trigger, say, visual sensations in lots of different ways. You can close your eyes, apply a little bit of pressure to your eyelid, and you'll see things. You'll see squares and circles and light and all that. There's no electromagnetic radiation falling on your retina, right? So it's not the stimulus that gives rise to the sensation of seeing. It is a particular kind, or the activity of a particular neural system. Now, the details of Müller's doctrine of specific nerve energies, Müller got the details wrong. He thought there was actually a different kind of energy carried by each of these nerves, and that's not right. All nerves have the same kind of energy going through them. It's an electrochemical process. But the general idea behind the doctrine of specific nerve energies is that sensory modalities are defined by a package of neural structures that are somehow specific to those modalities. Now, Müller was working in a tradition known as psychophysics. That's what the earliest psychologists were. They called themselves psychophysicists. And the reason I'm going to talk about this a lot is that what psychophysics is a very tightly controlled experimental version of introspection. What James did on himself, kind of more or less informally, Fechner and others did very tightly, in a very tightly controlled fashion in the laboratory. But the general idea is that psychophysics wants to trace the relationships between the physical properties of various sensory stimuli, physical properties that have what we would call a third-person objectivity. You can describe these things objectively, and the psychological properties of the experience to which those stimuli give rise. Those psychological properties having what we'd call first-person subjectivity. So you flash a light in front of me, or you play a bell and I hear a tone, or I hear the bell, or I see the light, or whatever. And what the psychophysicists tried to do was to search for evidence for what they called the psychophysical principle. The psychophysical principle being that every psychological quality of a sensory experience is related to some physical property of the corresponding stimulus. That's the psychophysical principle. So you measure the physical properties of a stimulus, you measure the psychological properties of the experience, and you see if there's some kind of lawful relationship between them. And of course there is, or I wouldn't be delivering this lecture. Well, how do they do that? Make a long story short, there were three basic methods that the psychophysicists used. One was a method known as just noticeable differences. They would present a stimulus to an observer, say a light of a particular luminance, and then they would adjust the luminance, take it down a little bit, increase it a little bit, until the observer said, I just now noticed a change. That's the method of just noticeable differences, okay? So you're looking at a change in stimulation. Or the method of constant stimuli, they would apply two stimuli to the person and ask him or her if there was a difference between them. Or in the method of adjustment, they give the person a little dial and that allow the person to turn the intensity, say, of the stimulus up and down until the observer just noticed a difference. By means of these psychophysical methods, what the psychophysicists wanted to do was to look at, was to determine thresholds for sensory awareness. That is, thresholds for conscious awareness. The general idea is that with respect to intensity, there's a level of physical intensity below which the stimulus doesn't give rise to any conscious experience, above which the stimulus does give rise to a conscious experience. And what you want to do is identify what that point is. That's the absolute threshold. The relative threshold is a little bit different. It is the point at which a person notices a change in stimulation. So you present a light and you turn the intensity of the light up just a little bit at a time until the person says, oh, it's changed now, okay? And you record that. As you can see, the absolute threshold is essentially a special case of the relative threshold because the absolute threshold is the threshold that makes the difference between nothing and something, okay? Whereas the relative threshold is the point at which something becomes something else. Okay, so that's basically what the psychophysicists were up to. And these guys really took the psychophysical principles seriously. Oswald Kulpe and E.B. Titchener actually tried to map out parallels between the fundamental properties in physics and the fundamental properties in psychology. So look at where these guys are writing, 1893, 1908. We're in a Newtonian world here, where the fundamental dimensions in classical physics are mass, space, and time. And the psychophysicists argued that there were psychophysical parallels to each of these. The psychological parallel to mass is intensity, how strong a stimulus is. The psychological parallel to space is extensity, how big the stimulus is, which is not the same thing. The psychological correlate of time is protensity, how long something seems to be. And then they ended up adding a couple of dimensions that they thought were unique to psychology and didn't actually have their counterparts in physics. One of these is atensity. Funny word, means vividness. They didn't say vividness because they were German. Atensity, besides you got to have something that ends in ty here. And then that's just, you can have something bright that's not very vivid, I suppose. You can have something that's dim that is vivid. That's a different thing. It's a psychological quality of a stimulus. And then you have our old friend, quality. Whether you hear something or see something, whether it's red or blue or whatever. So a lot of psychophysics was focused on the problem of intensity, okay? And if you think about it, that's a good place to start because intensity has to do with that point at which there is nothing and then there's something. You're not aware of anything, you are aware of something. And what they wanted to do was to develop means of measuring the strength of a psychological experience. So for vision, it's the brightness of a stimulus. For audition, it's the loudness of the stimulus. And the general idea was, the general hypothesis here was that brightness and loudness would be somehow related to the physical intensity of the corresponding stimulus. But precisely what that relationship was something to be determined. We won't talk about how this is coded in the nervous system, but the general idea is it turns out that there isn't an isomorphism between physical intensity on the one hand and psychological intensity on the other hand. The two don't vary together in a one-to-one manner, okay? Which is kind of interesting. The first guy to notice this was Ernst Weber, a German psychophysicist, who did a whole bunch of experiments of the sort that I just described and came up with what's now known as Weber's law, delta I over I equals C, which is to say the amount of intensity that must be added to a stimulus to produce a just noticeable change in intensity, a just noticeable difference. See it now, I didn't see it before, that kind of thing, is a constant proportion of the original intensity. Delta I over I equals C, a constant. So, for example, if C is 1/10 and the original stimulus intensity was 10 units, never mind what the units are, then you need to add just 1 unit of intensity to produce a just noticeable difference. Add 1 unit to allow the subject to be consciously aware that there's been a change. If the original intensity was 100 units, then you needed to add 10 units to produce a just noticeable difference. If the original intensity was 200 units, then you had to add 20 units, and so on. So again, there isn't an isomorphism here. It's not just that 1 unit is going to produce a just noticeable difference, whatever the original intensity is. What the change that produces the just noticeable difference is going to be a constant proportion of the original intensity. By means of Weber's law is very cool. You know, this is a really good place to start out. It's not often that you get a scientific law that sticks with you for 150 years. What happens is that the Weber fraction, that constant, 1/10 or 1/20 or whatever, can be used as a universal index of the sensitivity of a sensory modality. It allows you to compare the sensitivity of vision to the sensitivity of audition. It allows you to compare the sensitivity of human vision to the sensitivity of feline vision, or whatever, because everybody's got a Weber's fraction. So here we can see that for humans, anyway, visual brightness is associated with a very, very, very small Weber fraction. What that means is we're very sensitive to changes in brightness. It takes only a very small amount of change to produce a noticeable difference. For things like weight and thermal pain, also get relatively low Weber fractions. For loudness, a much bigger fraction. For things like the smell of rubber and the taste of salt, you really got to pile it on in order to produce a just noticeable difference. But the point here is that the Weber fraction gives you a universal index of sensory intensity. And that's nice. A colleague of Weber's by the name of Fechner generalized Weber's law into what is now known as as Fechner's law, which is expressed S equals K log of I, where I is physical intensity and S is sensory intensity, and the function here, that K is a constant, and then it's just the log of I. And what you get here is if you plot the intensity of the sensation S against the intensity of the stimulus I, what you get is a curve that's generated by a logarithmic function. Again, let's not get hung up on what kind of logarithm, natural or base 10 or whatever. This is the example. And what you can see here is that, yeah, just a little bit of change in physical intensity at low levels produces a big difference. You've got to have more change at other levels. But again, Fechner's law, S equals K log of I, is basically a generalization of Weber's law. It's a different way of putting it. And what happens is that if you then put this same relationship on a logarithmic scale, so you map the intensity of the stimulus on a logarithmic scale, you get a nice straight line. And these guys loved straight lines. Okay? All physical scientists, I think, love straight lines. But these guys were especially infatuated with the straight line because if you've got a straight line, somehow you really got something, right? Okay? Notice that there now is a one-to-one correspondence, you know, more or less. But it's a one-to-one correspondence only if you're dealing with logarithms. But the 19th century psychophysicists were very, very, very impressed with this, as well they should have been. But the idea here is that what we're doing is we're measuring something psychological. We're measuring something subjective. All we're asking the subject to do is to tell us when it changes or not. Assign a number. You can ask subjects to assign numbers from 0 to 100 to the magnitude of a stimulus, and what you'll get is this nice, lawful relationship. So that the fact that you got these nice, lawful relationships convinced the psychophysicists that they were onto something, that you could have a science of consciousness after all, because it was possible to tie conscious experience directly to the physical conditions of the world outside the mind. If you couldn't do that, then you might not be able to have a science of this at all. But the fact that you could tells you that you've got something that you can hook your the subjective reports on. The story isn't over, because it turns out that there are some interesting exceptions to Fechner's law. So for example, the perceived length of a line really does grow in a one-to-one correspondence with the actual length of the line. Okay? The important, I should have said this, the important point about Fechner's law is, Fechner's law can be stated verbally in the following way: sensation grows more slowly than stimulation. Okay? That's it. That's Fechner's law. Sensation grows more slowly than stimulation. There isn't a one-to-one correspondence, but there are these exceptions, and one of them is perceived length, where there is a one-to-one correspondence, and the other one is perceived pain, where it goes in the other way. Perceived pain grows more rapidly than the stimulus. And if you don't believe this, next time you're in the dentist chair having a cavity filled, ask the dentist to press down just a little bit more. Okay? The pain becomes much more excruciating than it has any right to be. So Fechner's law is good, but it doesn't cover all the bases. The law that covers all the bases was formulated by a Harvard psychologist, S. Smith Stevens, who brought the short Nordic ski to the United States. He introduced the short ski to the United States. So all you skiers out there, you have him to thank for this. And what Stevens basically did was to express Fechner's law not in terms of a logarithm, but in terms of exponents. Okay, so Stevens' law is s equals ki to the n. Okay, and the general idea here is that there's some exponent, okay, that relates the physical property of a stimulus to the psychological property of a stimulus. So again, if you assume that n is 1/2, 0.5, all right, the square root. Physical intensity is 1, sensory intensity is 1. Physical intensity goes up to 10, sensory intensity goes up only to 3.16. Physical intensity is 100. Sensory intensity goes up just to 10, and so on. This is Fechner's law. Sensation is growing more slowly than stimulation. Here's the case of length, where the exponent is 1, okay, exactly 1. All Fechner's law, the exponent is less than 1. For length, the exponent is 1. And for cases like pain, the exponent is greater than 1. So here, physical intensity is 1. If the exponent is 1.5, physical intensity is 1. The square root of the cube of 1 is still 1, okay? Physical intensity grows to 10, sensory intensity goes to 31.6, grows more rapidly than stimulation. That's Stevens' law. And Stevens' law is generally assumed to be a kind of general purpose psychophysical law. It applies in unbelievably large numbers of domains of sensation. It's almost as close as we can come to a universal law in psychology, Stevens' law. It's so good that you can study juries, for example, and you can look at the amount of money a robber has stolen or the number of people he's killed, okay, and look at the sentences recommended by juries, and those sentences will follow Stevens' law. There's an exponent that relates the amount of money you've stolen as a robber to the sentence that the jury wants to give you. It's really, really cool law that has applicability way outside the sensory domain where we're focusing our interest. Okay, so the point here is that 19th century psychophysics qualifies as our very first scientific approach to consciousness, okay? What these guys did were, they didn't just introspect, they didn't sit in their armchairs and look inside their minds. They did empirical studies, just like psychologists do today, based on systematic observation and controlled experimentation. They employed quantitative, not qualitative data. They engaged in various kinds of mathematical and statistical analyses, and they expressed their results in terms of various kinds of mathematical functions, whether it's Weber's fraction or Fechner's law or Stevens' law, doesn't really matter. Mathematical functions that relate something that's going on in the world outside the mind, in the stimulus environment, to a person's conscious sensory experience. All of psychophysics is like that. Now, so far, I've focused on intensity, but of course, there are qualities of stimuli, qualities of sensations besides how intense they are. And the 19th century psychologists gave us our first scientific approach to that as well. Intensity is a quality that is common to all sensory modalities. Some smells are stronger than others, some tastes are stronger than others, just like some sights and sounds are stronger than others. But the psychophysicists also wanted to get psychophysical laws that would apply to specific qualities that are specific to a particular modality. So, for example, in vision, we have qualities of hue and saturation that occur only in vision. They don't occur anyplace else, except maybe by metaphor. And in audition, we have qualities of pitch and timbre, which also occur only in audition. They don't occur anywhere else. And the psychophysicists tried to map the relations between these qualities and the physical properties of stimuli as well. So, for example, when you look at the qualities of visual sensation, hue seems to be related more or less regularly to the wavelength of light that's stimulating the person. If you've got relatively short wavelengths, you get blue. Long wavelengths, you get red. Medium wavelengths, you get something like a green or yellow. So that's a psychophysical relationship. Perceived color, hue, is related to the wavelength of the stimulus. Saturation, the difference between this pure red and this kind of pinky color here, has to do with the amount of gray that's been added to the stimulus. So again, there's a psychophysical law, a psychophysical relationship that relates how saturated you experience a stimulus as to some physical property, how much gray is in there. Yes? Yeah. Well, when we talk about intensity, it's best to think about it in terms of pure colors. Red, green, yellow, blue, whatever, that don't have any gray in them at all, okay? So what you've got is the pure color, okay, no gray, how bright or dull is it? Now, this is going to look, I suppose, less bright, okay, than this does. But it turns out, if you're a psychophysicist, I'm just a crummy guy with a PowerPoint presentation here, but it turns out you can do these experiments so that you can keep the brightness constant, but vary the saturation. You can keep the saturation constant, but vary the brightness. And that's what they did, to kind of get these things down. So, for example, this is probably the first of about 100 cat examples you will get from me. The cats have basically only rods and no cones in their retinas. Not quite true, but it's pretty true, leading to the idea that they can't see color. But it turns out cats do appear to respond to stimuli of different colors, but what they're really responding to is different saturations. If you can keep the saturation constant, you see that cats don't discriminate between colors. So there is this difference. It's orthogonal. It's a little bit hard to demonstrate in just a single slide. Nice question, however. Okay, so similarly, for qualities of auditory sensation, pitch is related to the frequency of mechanical vibration. So you've got middle C on the scale, corresponds to about 262 cycles per second. Second space C in the bass clef, 131. Third space C in the treble clef, 523. That's a psychophysical relationship. And timbre corresponds to the shape of the sound wave, how jagged it is or how smooth it is. Flutes, for example, have pretty smooth sine waves. Okay, oboe, which is much more raspy, has a lot more jagged quality to it. That's basically the idea here. Again, these are qualities of sensation, qualities of experience that are related lawfully to some physical property of the corresponding stimulus. Okay, which gives rise to what Hermann von Helmholtz called the doctrine of specific fiber energies. Helmholtz was a student of Müller's, and in the same way that Müller had this idea that every modality of sensation is mediated by a specific neural system, so Helmholtz had the idea that every quality of sensation within a modality is mediated by a specific neural system. So, for example, Helmholtz did a lot of work on audition, and he discovered that the inner ear has fibers that respond specifically to high versus low pitches. Okay? And we know, for example, in vision, that we have 3 different kinds of cones that are roughly responsive to low, medium, short, medium, and long wavelengths. Yeah?
Is there a difference between sensation and perception?
Yes. We're not there yet. Okay? Here's the difference, though. For sensation, what you're really doing is detecting the presence of a stimulus. Okay? Perception has to do with identifying the form, the location, the activity, the category, the meaning of the stimulus, actually forming a mental representation of what the stimulus is. So you could argue that the act of perception isn't really completed until you've identified and categorized the stimulus. Here, we're talking about as pure sensation as we can possibly get, okay? Lights in a dark room, tones being presented against a background of noise, stuff like that, where there's nothing to perceive. You're just detecting the presence of a stimulus. That's the general distinction. Okay, so now what we can do is we can try to figure out how these other qualities of sensation besides intensity kind of get built up. This wasn't so much the task of the psychophysicists, but it was a task that was taken up by another group of 19th century psychologists known as the structuralists, like Wilhelm Wundt and his American student E.B. Titchener. And what Wundt and Titchener argued for was what Wundt and Titchener called a mental chemistry. The idea behind structuralism was that you could think of conscious experiences as somehow analogous to chemical molecules. And that these molecular level experiences could be analyzed in terms of their structural elements in the same way that if you're doing chemistry, you can analyze a molecule into its constituent elements. So what the structuralists tried to do was to present people not with pure tones or lights in a dark room or whatever, but with something more complicated, right? They'd show them a picture of something, or they'd have them taste some spice or whatever, and ask them to analyze their sensory experience into its constituent elements, by which they meant elementary sensations, feelings, and, well, there was a debate about images, but we're just going to talk about elementary sensations now. So the idea behind structuralism was that we could identify the basic qualities of sensory experience, those qualia that I talked about in the last lecture, by doing this kind of very carefully controlled introspection, okay? And when you do this, you had to do something very weird. Wundt or Titchener would present subjects with a complex the stimulus, and then ask them to describe their experience, but not to describe the stimulus, okay? So I could hold something up and say, well, tell me, you know, what your sensory experience is here. And you'd say, well, it's a notebook and it's kind of thick and geez, are we gonna get through all of that in 14 weeks? That's the stimulus error, right? You're describing this thing. What you're supposed to do is describe your experience. Well, it's blue and it has this and it has that. Whatever it is, you're supposed to focus on your, you're not supposed to make any inferences about the object. You're supposed to describe your experience when you're observing the object. This is not an easy thing to do, and you had to be very carefully trained to do it, but the structuralists were able to do this with some success. So, for example, they discovered that, as we already knew from work earlier in the 19th century, that any particular color could be analyzed into some combination of 4 primary colors: red, green, yellow, or blue. You put up a purple color swatch and the person will say, well, you know, I see red and I see blue. You put up an orange color swatch and the person will say, well, you know, I see red and yellow and so on. These primary colors were discovered in pretty much this way, leading to what's known as the trichromatic theory of color vision, a theory that is not right, but we're not there yet. We're not going to get there, actually. But in the 19th century, the general idea here was that all visible colors can be produced by some mixture of just 3 primary colors: red, green, or blue, if you're looking at additive mixture, or red, yellow, and blue if you're looking at subtractive mixture, which led people to postulate that there must be 3 different kinds of cones. One type relatively sensitive to short wavelengths, blue light, we'll call it. Another one relatively sensitive to medium wavelengths, we'll call that green light. And another one sensitive to long wavelengths, we'll call that red light. Now, the trichromatic theory is wrong, okay? It was replaced by a much more interesting opponent process theory. That's for a sensation and perception course, not for here. But the general idea here is I want to use the trichromatic theory to give you a sense of how these guys did their work. Okay. Now, this is important because more recent psychologists, like Cornell's James Cutting, have argued that the quest for primary colors, red, green, blue, whatever, can serve as a kind of model for the quest for primary qualities of sensation in other sensory domains. And Cutting has this wonderful paper in which he says, look, one thing that the primary colors do, that you'd want basic qualities to do, is to have a situation so that the physical mixture of primary qualities would yield all other qualities. And that's true. You can get all visible colors out of, all visible hues out of some mixture of red, green, and blue. And Cutting argues, well, if you've really got basic qualities of sensation, there ought to be what he calls physiological attunement. There ought to be unique neural pathways for each of these elementary qualities. So if red and green and blue are elementary qualities of vision, then there ought to be unique neural pathways for them. If orange and yellow and purple are not, then there won't be. Okay? Again, this is in line with Müller's and Fechner's doctrines. Moreover, Cutting points out that primary colors are monolexemic. They are expressed in just a single word, okay, red, green, blue, and these are words that have high frequency of usage in common discourse. Okay? And you ought to have these basic categories encoded in most languages, and that's true for the primary colors. All languages, if they have color terms at all, have terms that correspond to black and white. Maybe it's dark and bright, but it's essentially black and white. And then if they add color terms, they usually add red and yellow, and either green or blue are primary colors. And then later on, they add other kinds of things. And then Cutting points out there's something special about these primary color words, red, green, blue, yellow even, and that is that those words, black and white, don't refer to any specific object, okay? Whereas mixtures like orange and violet and olive are color terms that are borrowed from objects that have that color. So if you take the primary colors as a model for primary qualities in other the modalities, you have some sense of what kinds of features these primary qualities should have. So if you want to know, gee, do I have the basic qualities of touch or audition or whatever? Cutting's argument is see if it fits these kinds of qualities. And it turns out that you can do this. We're going to do this real fast because there's nothing to show here. Hanig and Henning, around the turn of the century, argued that there were 4 basic qualities of gustatory experience, 4 basic taste qualities: sweet, sour, salty, and bitter. Everything else you taste, the taste of your Snickers bar, your tofu, whatever it is that you're eating, is some combination of these 4. More recently, now that people are eating Chinese and Japanese food, added a 5th taste quality, umami or savoriness. But the point is that any particular taste could be located as a point within this taste tetrahedron, where you've got these basic dimensions of salty, bitterness, sweet, and sour. These are arguably the basic qualities of taste. Similarly, you can look at these are the introspection has suggested, these are the basic qualities of olfactory experience. Whatever it is you're smelling, that smell is some combination of spiciness, fragrance, etherealness, resinous, putrid, and burn. And you can locate any particular taste as a point inside this space. Skip that. Edwin G. Boring, Titchener's most famous student, did the same thing for somesthetic experience, qualities of touch, and argued that these were the basic qualities: pressure, pain, warmth, and cold for sure, maybe roughness and wetness as well. Here's Titchener's own work on this, what's known as the touch pyramid. Again, the idea here is you've got these basic qualities of tactile experience, and any particular quality, sandpaper on your skin, silk on your skin, okay? Whatever that quality of sensation is, it can be located as a point within one or another of these spaces, okay? Do the same thing for emotion. Wundt didn't just look at sensory experience, he also looked at affective states, and he argued that any emotion that you have could be located in a 3-dimensional space where the dimensions were pleasantness, strain, and excitement. It's probably not right, but that doesn't matter whether it was right or not. What matters is structuralism, 19th century structuralism, tried to take up directly this problem left to us by the philosophers and articulated so nicely by Nagel. What is it like to see purple? What is it like to taste 5-spice powder? What is it like to feel satin on your skin? That question is a question of the basic qualities of sensory experience. And the 19th century psychophysicists and the 19th century structuralists, by addressing that concept directly, gave us our first scientific approach to consciousness. Okay, next time we'll take a look at the mind-body problem and where that takes us. Thank you very much. Remember to go to section this week. Have a good weekend.
Yes.